Hello students, welcome back. In this video we are going to go through section 9.3 to dependent samples. So now we are presenting methods for testing hypotheses and constructing confidence intervals involving the mean of the difference of the values from two populations that are dependent. So last section the two samples that we analyzed were independent. They had no relation. Now we are looking at ones that are dependent, or they have some kind of relationship. So the pairs must be matched. So just some conceptual examples are, say you're looking at body temperatures of people. So, and then you measure them two different times during the day. So the two samples will be body temperatures at 8 a.m. and body temperatures at 12 a.m. So each of these data values are paired. Because it's the same person, they're not independent. They're related. There's a relationship. It's the same individual. Another example is a very random topic, but the number of words spoken in a day by each member of 6 different couples. And then the heights of mothers and daughters. So each one of these are a pair, and since the height of a daughter is going to be related to the height of the mother, they are not independent, they are dependent samples. So once again, we're going to be doing a hypothesis test and a confidence interval. So here are the notation. So the new symbol here is lowercase d, which is going to be the difference, d for difference. So d is the individual difference between the two values in a single matched pair. So there's going to be several different d values. There'll be a d value for each one of these individual, where's my cursor? A d value for each of these individual pairs. There's also going to be mu d, which is the mean value of the differences for the population of all matched data pairs of data. D bar is going to be the mean value of the differences d for the paired sample data. So you have all your individual differences. So you can almost imagine there being like a third row right here just showing you what the difference is. Those would be all your d values, and then your d bar would be the mean of the differences. Your SD is going to be your standard deviation for the sample, and N is going to be your number of pairs of sample data, not individual cells, but each pair is going to be representing your N. So here are your requirements. Nothing new or crazy for that, so we'll just kind of skip it without wasting your time reading it. Okay. So we are going to be making inferences about the differences. So we're making inferences about the differences between each matched pair. So our equation for the test statistic for the dependent samples is going to be this equation right here, with our null hypothesis being mu of d equal to 0. So this is your important equation right here. Notice how it differs from one test sample and the two test samples we did in the previous section. It's a different t value, a different test statistic equation. So your p-values are provided by technology or table A3. And then once we get this t-statistic, we can do a simple t-test like we did in chapter 8 for the one mean as opposed to the two sample means in the previous section. So basically, to kind of summarize what I just said, we're taking two paired sets of sample data. We are using it to make one t-value by pooling them together by each individual matched pair of values, and then we're doing a simple t-test like we did in chapter 8 as opposed to the two sample mean we did in section 9.2. So critical values, similar concept. Degrees of freedom is n minus 1, table A3 for the distribution. And your confidence interval right here is a simpler one from the previous section. We just have our d bar minus the margin of error, and then is the lower limit, and then the d bar plus the margin of error is your upper limit, with your null hypothesis being in the middle. And here is your equation for your margin of error. So here is your procedure for making inferences with dependent samples. So first, verify that the sample data consists of dependent samples. Well, that should go without saying. Find the difference D for each pair of sample values. So you take the one, subtract it from the other. That will give you the D for each individual pair. Once you have the D for each individual pair, you have to find the mean of all of those data values and then the standard deviation of all those data values. And then once you do that, you can move on to step 4, which is do the hypothesis test and confidence interval for the same T procedure used for a single population mean. So these are actually a little easier than the process we did in section 9.2, where we dealt with independent samples. So similar to 9.2 as well, because we're using the same distribution and standard error, hypothesis tests, which consists of p-value and critical value, and confidence interval are all equivalent in that they will always give you the same conclusion. So here's our example. Once again, I want my example to be solved several different ways, and even the way as I give you, you can do several other ways. So I'm showing you with the TI-84, you can easily use StatCrunch, StatDisk, Minitab, Excel, the book. Did I show you a slide? I think I showed you the slide that tells you where you can find the step-by-step directions in your textbook. But if not, just skim through your textbook. They always have a pretty good section giving you a step-by-step. So this example says, are best actresses generally younger than best actors? So the data lists ages of actresses when they won Oscars, along with ages of actors when they won actors in the category of Best Actor. So the ages are matched according to the year that the award was presented. So this would be year 1, year 2, or sure, whatever. So this is a small random sample. So we obviously we want to use more if we want to get more accurate, but we'll proceed. So use the data sample data with a 0.05 significance level to test the claim for the population of ages of best actresses and actors. The difference levels have a mean less than 0. So here is your row 1, here's your row 2, here's your differences. You're just taking this, subtracting this value. Here are your 5 differences right here. So right now we just did step 1 and step 2. So we have to do step 3, which is find the mean D bar and the standard deviation of the sample. So requirement check, good. Your null hypothesis is going to be that the mu of the sample, mu of D, mu of the difference is going to be equal to 0. And then since we're looking for a less than, the null hypothesis, the alternative hypothesis is going to be the original claim, which is that the mu D is less than 0. So we have to now find what the mean and the standard deviation of the samples are. You could use that by finding a list on your TI-84. Here's a quick summary. I went through it a little bit more in depth in the previous section, and you get a sample statistic of D bar equals negative 10.2 years, and the standard deviation of 14.7 years. So using these sample statistics and the assumption from the null hypothesis, we find our test statistic, and the value we get is negative 1.557, and I'll show you work on the next slide since your textbook doesn't think that they need to tell you how you got it. They just throw that number out to you as if you're all going to know how to do that without a quick reminder. So I'll show you how to do it without technology first. So we previously determined these values right here. Here's our equation. You plug it into your calculator. Boom, there's your value. With technology, actually in this case the technology seems to take even more time, but it's a safer bet. So we determined that the D bar is negative 10.2, and we will treat this as X bar for calculator input. Same with our standard deviation. Even though it's S of D, we will treat it as S of X for calculator input. So we press stat, the right arrow twice to go to tests, and then 2 for T test. Again, the same thing we did in chapter 8. And then we're going to go to stats. Our null hypothesis is going to be 0. Our x bar is now going to be negative 10.2. Standard deviation 14.7. N is 5. And we are doing this tail test. Go to calculate, hit enter, and then we get our t value this way as well as our p. So because we are using a t distribution, we refer to table A3 for the row with degrees of freedom of 4, which is 5 minus 1, 5 being the number of pairs we have. And we see that the test statistic of t equals negative 1.55 corresponds to an area in one tail that is greater than 0.05. So p-value is greater than 0.05. Technology provides it as 0.0973, which we got when we did it. Something similar. I guess they use a different program that gave a slightly different p-value, but pretty close. Okay, so our test statistic is here, and we have a p-value of 0.0973. Now looking at the critical value method, refer table A3, we find the critical value of t equals negative 2.132. So if we use the p-value method, we fail to reject our null hypothesis, since the p-value is greater than the significance level. If we use the critical value method, we fail to reject the null hypothesis because the test statistic does not fall within the critical region. Critical region right here in the green value. Our test is not within the green region, so we fail to reject it. So our conclusion, we conclude that there is not sufficient evidence to support the original claim. There is not sufficient evidence to support the claim that for the population of ages of best actresses and best actors, the difference have a mean less than 0. There is not significant. This is so redundant the way you have to read these. There is not sufficient evidence to conclude that best actresses are generally younger than best actors. Maybe that wouldn't be the case if we had more data samples, since I feel like I know more famous older male actors, but maybe that's just anecdotal for me. So finally, we just solved it from the p-value and the critical value. Now we have to do, you guessed it, the confidence interval. So same data sample, construct a 90% confidence interval. So because we are doing a hypothesis test for a one tail with a significance level of alpha is 0.05, the confidence level we're going to do as 90%. So here's showing you a summary of the stat disk, but I'm going to show you doing first without technology, then with. So here is your margin of error equation that I showed you earlier, and you get a value of 14.01, which is a very large value. So again, that's because of how few data values we have, and it's only 5. So then we find the confidence interval from using this equation right here, and then we get the lower limit is negative 24.2 and the upper limit of 3.8 years. Again, since this is a negative number and this is a positive number, 0 is going to fall in between. Now showing you with technology, hit stat, go over to tests, press 8 for t interval, type in your values as you see here. Go to calculate where it's highlighted right here, hit enter, and then here's the same values over there. And then we have a 90% confidence that the limits of negative 24.2 and 3.8 contain the true value of the mean. So the confidence interval includes the value 0, so it is possible that the mean of the difference is equal to 0, indicating that there is no significant difference between the ages of best actresses and best actors. So as with other samples, like I tried finding this slide a little bit earlier, your textbook provides step-by-step instructions for several other ways. I encourage you to try them. At least try StatCrunch. Some people find that easier. go to page 447 and 448, and it gives you step-by-step to how to solve the same problem just using these different software programs. And that concludes section 9, or chapter 9, section 3.